Well, grade 12s, in this lesson, what we want to do is I just want to recap what we did in the previous lesson. If you take, for example, you've got a parabola, okay, a curve. There it is. And it's there, and it could be, let's say, fx is equal to x squared. Okay, no problem, we'll just make up that one. Now, we pick a point on the curve. Let's say x is equal to 2. For example, the corresponding y value is 4 because the f of 2 is 2 squared, which is 4. Great, so that's your y value, the f of 2. But when we draw a tangent to the curve at x equals 2, we now talk of the gradient of the tangent at 2, okay, which is going to be, very simply put, the gradient of the curve at 2. Okay, and we used first principles, the limit as h goes to 0, etc., to work out that gradient of the tangent. But you probably agree with me that that's very tedious to do that whole process of the limit as h goes to 0. You have to do it once in an exam, but surely there must be other ways of doing it. And by the way, let me just quickly also explain to you that when you talk of the word gradient, there are other words that can be used for gradient. The one word is slope. Okay, the other word is called a rate of change. When you talk of a rate of change, you talk of gradients. And the other one is the word derivative. So if they use the word derivative, rate of change, or slope, it really means the gradient. Okay, and remember the limit as h goes to 0 of fx plus h. This little limit is determining the derivative, the rate of change, the slope, the gradient from first principles, and you always get to do that once. Okay, so that's first principles. And some other symbols that we use, we've used f prime x, which represents gradient. There are other symbols, dx, you'll see we're going to do a lot of those, and also dy over dx, other symbols that all mean gradient. Okay, and we're going to be looking at that in a lot of detail. Okay, now what I want to do is I want to explore what we call the rules of differentiation. Now these guys, these rules make finding the gradients a joke. They bypass first principles in such an incredible way. And if you remember, when you use the limit as h goes to 0 of fx plus h minus fx over h, you're doing gradient from first principles. But now, is there an easier way to do this? Definitely. The first rule, and I'm going to show you exactly how this works by looking at previous things that we've done. If you look at the first rule, it says if you've got an fx is equal to ax to the exponent n, the derivative, the gradient, the slope, the rate of change, the gradient of the tangent to the curve, or the gradient of the curve itself, can be determined as follows: a multiplied by n x to the n minus 1. So what we do is we write the exponent, multiply it to the a, and then subtract 1 from the original. Now, for example, if you had fx is equal to, let's have a look at x squared. Now, if you remember in the previous lesson, the gradient was determined by first principles, and that gradient, the answer was 2x. I don't know if you can remember that, but we got an answer. But if you apply the rule 1 of differentiation, what it says bring down the 2 and subtract 1 from the original, which gives you 2x. If you've got a thing like this, if you have fx is equal to, say, 3x to the 8, the same principle applies. The gradient, the derivative, the gradient of the tangent is 3 multiplied by 8, x to the 8 minus 1, which of course is 24x to the 7. Okay, that is the rule for determining it. And why it works, it's actually quite interesting as to why it works. If you have a look at this, say for example I said fx is equal to x squared, and we did first principles. We went to fx plus h, and we simply went ahead and did first principles. This would come to, of course, x squared plus 2x plus h squared. Then we worked out the derivative, the gradient, the slope, the limit as h approaches 0. Fx plus h was this guy. Remember, I'm doing first principles now. Now watch this. Subtract the fx, which is the x squared, divided by h. The x squareds cancel, and you have the limit as h approaches naught. The x squared have cancelled, and you take out the h, and you're left with 2x plus h over h. The h's go bye-bye, and we're left with the limit as h approaches naught of 2x plus h. Now that comes to 2x plus naught, which of course is 2x. Now have a look at this. If you have a look at the gradients here, if you look at this, x squared, the derivative is 2x, the gradients of the curve, the gradients of the tangent to the curve, the rate of change, the slope, anywhere on the curve. Okay, so you can immediately see that that's quite an interesting little principle there. It bypasses first principles. There's another rule which is quite easy. If you take fx is equal to ax, okay, that's just like a normal straight line. If you apply rule 1, you could say a, well, that's a 1 there, that's going to be 1x to the 1 minus 1, which is a x to the naught. X to the naught is 1, so it's a times 1 is a. And in other words, if you look at this, I think it's actually quite easy just to go from here. If you said fx is equal to ax, because this is like a straight line graph, the gradient is in fact the coefficient of x, which is a. So you can go straight from there to there. An example would be if you have fx is equal to, for example, if you take 10x, well, what's the gradient of that line? Is just 10. Okay, so that's another rule. And then the third rule is quite fun. If you have a look at the third rule, what the third rule in calculus says is if you've got fx is equal to some kind of a number, the gradient or the derivative is naught. Think of an example. If you had fx is equal to 7, that's the graph of a straight line, a horizontal line cutting at 7, y is equal to 7, and if you remember from earlier years, the gradient of a horizontal line is naught. So fx is equal to number. By the way, what they can also often say is they give you this. They say fx is equal to, for example, they might say fx is equal to p. Okay, and they say p is a constant or something like that. Well, what you can do is you go f prime x is naught, because that is a constant. It's some number you don't know, but it's a horizontal line. So the gradient of that. So anything that's a number or a letter which is not x, the gradient will go to naught. Okay, now let's have a look at some examples dealing with these three rules. Okay, have a look at this. If I said determine the derivatives of the following, or the gradients, and I'm going to give you that, the one that we did from first principles in the previous lesson. And if you remember, the answer came to negative 4x. Okay, now if we apply rule 1 to this, watch this, f prime x is equal to negative 2 multiplied by, now what do? We bring that exponent up top there down and subtract 1 from the original. This guy is actually rule 3. It just goes to naught. Okay, it's a number. So your gradient or your derivative is negative 4x. And that's what it was when you did first principles. Okay, another one, for example, let's suppose you had fx is equal to 3x. Well, no problem. That's a straight line graph. The gradient of that line is 3. You can go directly to that, no problem. Okay, and what about number C? This is going to get a little bit more interesting. What if we have a hyperbola like 1 over x? Well, what we could do is that's not quite in the form ax to the n. We don't have it looking like that. But what we could do is if you bring that up, you could get x to the negative 1. So it's actually 1x to the negative 1, which looks like this now. So then you can say f prime x is equal to 1 multiplied by, bring down the negative 1, x to the negative 1, and you always subtract 1. And then have a look here. This becomes f prime x is equal to 1 times negative 1 is negative 1, x to the negative 2. And of course, if you want to make the exponents positive, then all you have to do is this. You can say that's equal to negative 1 multiplied by 1 over x squared, and then negative 1 times the 1 gives you, of course, negative 1 all over x squared. And that is your gradient if you use the rules of differentiation. Okay, and then number D, have a look at this. If it's quite a difficult one, like say for example x to the 100, well, the gradient of this, thank goodness we don't have to do first principles on that. That would be a lot of brackets, is 100 x to the 99. You subtract 1. That is the gradient of the curve there. Now you may have different notations as well, people. Now I'm going to show you how to use the different notations. If they said to you, for example, they give you fx is equal to 3x to the 6. That's the one way of doing it. The derivative would be, of course, 3 multiplied by 6x to the 5. That's the first rule. Bring down the 6 and subtract 1, which of course gives you 18x to the 5. That's one way of doing it. But some books, what they'll do is they'll say, determine the derivative of the gradient of the graph y equals 3x to the 6. Now, for the symbol y, when you want to get the gradient, we use this notation. Look at that. dy divided by dx. And then you do exactly the same thing. You bring down the 6 and subtract 1 from the original. So that's a different way of saying the same thing. A third notation that they sometimes do, they say, work out the derivative like this. Okay, now dx of that. Now you've already got the dx there, so when you do the dx, it's like the limit symbol. You drop it, and then you go 3, 6x, 5, and the answer is 18x5. Look at the notations, one for fx and one for y. Fx, f prime, y, dy, dx, and then the other one is just dx of that thing. Gives it to you there. It's one notation that can happen there. Let's have a look at this if we look at another one quickly. So you've got all of that kind of thing. A second example, let's have a look at this. If you have, so I said to you, take fx is equal to 3x. What's the derivative of that? Well, according to rule 2, it's the gradient of the line, which is 3. If I said to you y is equal to 3x, and you want the derivative or the gradient, you use the dy dx notation. If it's just dx of 3x, then you just simply work out the gradient there, and there you've got it there. Okay, and then also it works the same if you've got like with rule 3. If I said to you, if fx is equal to 3, or if y is equal to 3, or what is the dx of 3? Well, in this case, f prime x is 0. That's the third rule. dy dx is 0. Remember, it's just a constant, and that's 0 there. It's a constant. Notice fx, f prime, y, dy dx, and then just dx works like that. And then another one, let's have a look at this one. Say, for example, I said to you, if fx is equal to, watch this, px squared plus px plus p, and I said, determine f prime x. Well, no problem. What we do is we apply rule 1 here. We bring down the 2 and subtract 1. This is rule 2 here, which is just p, the coefficient of x. That's what's the gradient of px is p, and this is a constant, which is 0. It's got no x in it, so it goes to 0 there. And our answer comes to 2px plus p. That is your derivative, your slope, your rate of change, your gradient of the curve, or the gradient of the tangent there. Okay, and so be aware of these 3 rules. They're definitely a lot better than first principles.